today's webinar, we're going to take a look at some of the supports that Maple has for a Precalculus trig course. I assume that you've read the abstract, so I'm not going to repeat what's there. But before I start, I want to ask the question, what is Precalculus? Well, here's a possible answer. It's been provided by a leading publisher. This is the table of contents. If expanded and printed, this table of contents would run some 10 pages. There are 15 units, and these units, inside each unit, there are chapters. There are 95 chapters. Inside each chapter, there are sections. There are 368 sections. This is a massive text. My advanced engineering math book, which ran some 1,200 pages, had just 9 units, 48 chapters, and 273 sections. I don't know how one could fit this much material in a 1 or 2 semester course. I think the material that I've looked at, I've expanded this and looked at what this was. It looked like it was all the math I learned in high school and a college algebra course that I took at the beginning of my college career. But that's going back to the mid-50s, so that's a long time ago. Now, I think that the only way that a student can absorb this much material or get a handle on this much material is they got to use technology someplace. Now, believe the authors of a book like this must agree with that, because they talk about graphing utility. So maybe they're talking about graphing calculator. But I think I would prefer Maple, and I want to show by means of the examples that I've selected why I think Maple is a good choice. Okay, for our first example, let's just look at a simple linear equation. So the problem here is to solve this linear equation in one variable. So let's begin by getting a graphical solution. So I'm going to bring this equation down to where I can work on it. So I highlight it, I hold the control key down and pull it into place. I call that a control drag. That's not a Maple thing. It's a Windows thing. I'm in Windows. You can do the same thing in Linux and on a Mac. In the context panel over on the right, you see plot both sides. So each side of this equation is a linear function. I click and I get a graph of the two sides. I'm looking for the intersection. Now, if I right click on the graph, I have some pop-up items I can do. So it says probe info. If I go down here to one of these, I pick nearest datum. So it's searching the database and finding the nearest point, and you can see the coordinates of the intersection. It's like a trace on a graphing calculator. So if I again right click and go to probe info, it says copy the data point. I'll find a place over here to paste it. Control V, paste. So I paste in the coordinates of this point of intersection as a column vector. Here's the X, there's the Y. Well, what about an exact solution? Well, again, we need the equation. Close that, bring this over with a control drag again. In the context panel, we find a solve, and the simplest solve will work. The answer is X is 9/2. Now, can we get a stepwise solution? Well, we'll go here to Tools, Load Package, and install the Student Basics package. And then we'll bring down the equation again. And if we go here to the context panel where it says Student Basics and select Solve Showing Steps for X, Maple solves the equation and annotates the steps that it went through to obtain that solution. Add 7 to both sides, subtract 3x from both sides, divide by 2. Now what about getting a more hands-on, student-involved solution? So here, let me close some of this stuff up and solve the equation the way you would do it with a pencil and paper, moving stuff around on the screen. So for example, you want to move the 7 from the left to the right, you add 7 to both sides. So you grab it and pull it over. You see that pop-up says add? Yeah, add 7 to both sides. Now you want to subtract 3x from both sides. So drag it over and you have the option to subtract 3x from both sides. Then you want to divide by 2, so select the 2, drag it over. It says divide by 2. So here is a way of manipulating the equation kind of the way you do it with a pencil and paper. And finally, let's make use of the equation manipulator, which is a tool that allows the student to solve the equation in this same dynamic way, interactive dynamic way. So again, we'll begin with the equation, and over here in the context panel you see the option manipulate equation that launches this tool called the equation manipulator. Stretch this out a bit, and as we do stuff, we want the steps to be one under the other, so I will check that box. So what do we have to do first? Well, we want to add 7 to both sides. Well, that option is visible here. Add 7 to both sides, and now you want to subtract 3x from both sides. So you add a negative 3x to both sides. Finally, you want to divide by 2, and you would accomplish that by multiplying the equation by 1/2. Do that, and there you have your x equals 9/2. And if you return steps, you will get the steps that you just went through. They're not annotated, but you get a record of the steps that you just went through. For a second problem, let's solve a quadratic equation. So we have this quadratic. We would like to get its roots analytically, graphically, numerically. To obtain a graphical solution, let's bring the equation down as we've done. First problem, Control drag it down, and here you have in the context panel the option plot both sides. It would be better to have this graph, let's say between 0 and 5. So right click, pick axes, properties. So instead of going from -10 to 10, let's go try 0 to 5 and see what that does. And also notice, because of the -10, we're way up here at 160. We should make an adjustment to the vertical axis. How about -2 to try 4? See if that works. So let's apply that. Yes, that's fine. You can see that one solution is slightly bigger than 1.1 and slightly less than 1.5 and slightly less than 4.5. So you can also read some coordinates here. Right click, probe info, pick nearest datum, set the crosshairs on one of the points, read off the coordinates of that crossing, and similarly for the other side. To get a numeric solution, again, we'll need the equation. So I'll grab it from here, Control drag it down, and in the context panel you'll find a solve and a numerically solve, and there are the two solutions. One is slightly greater than 1.5 and the other one is slightly less than 4.5. An exact solution can be found from the context panel using solve option. So we need the equation and solve. Two solutions, 3 plus or minus the square root of 2. And finally, an exact solution from first principles. So we need a copy of the equation. Control drag it down. And we'll use the equation manipulator to do that. So we've launched the equation manipulator. Check this box so the steps are written one under the other. The way I would teach a student to do this is get rid of this 7 first. Don't be juggling half the square of the middle term, the linear term. Then you got to add it to this and add it to here. Too much overload. Get rid of the 7 first. So add a -7 to both sides. Now add 9 to both sides. Well, you won't find add 9 to both sides in here because Maple doesn't expect you to be solving this thing from first principles. So let's just add 9 to both sides. Now the left side is a perfect square, and you want Maple to write it as a perfect square. So select factor, apply it to the left side, and now it's time to take the square root of both sides, and you have an option down here, take the square root of both sides, and a dialog comes up. Which root do you want to look at? Well, we'll pick the first one to start with. So in order to isolate the x, add 3 to both sides, and you have the first root, 3 plus root 2, to get the other root. The simplest way to do it, in my opinion, is to back up 2 steps, take the square root of both sides. Now pick, I squared both sides. We have an undo here. Take the square root of both sides, pick the other root, select that, add 3 to both sides, and now you've got 3 minus the square root of 2. And if you click return steps, you'll get a list of the steps that you went through in order to solve this problem. Now I noticed that in some of these newer precalculus books, there's a lot of emphasis on functions. Well, one of the things that they do with functions, the study of functions, is to see how their graphs behave under various transformations. So here is a problem where we take any of the elementary functions, right, and we see how their graphs behave under the transformations induced by a times f of b x minus h plus k, where a, b, h, and k are parameters that can be modified. To tackle this, we'll make use of a tutor. The tutors are a bunch of pop-up tools that are housed here. Tutors, and ours is in Precalculus. It is this standard functions tutor. I've got it rigged so that clicking this button will launch it. This is the standard functions tutor. All of the elementary functions are accessed in this drop-down. The default settings for the parameters a, b, h, and k are 1, 1, 0, 0. So here is sine x without any transformations. Now, if you want to apply some value of h, which is not 0, put in some number, try 3. So what happens is the original sine curve stays in red, and the transformed graph shows up in blue. If you want to give k a value, give it 3. The curve is raised. If you now say, well, what happens if we go back and let h be 0? Then you get the vertical shift of the sine curve up. So with this tool, you can explore the meaning of these parameters a, b, h, and k. Another application of the idea of a function is the notion of the inverse function. So here's a problem where we explore meaning and computation and visualization of an inverse function. The function we want to invert is this one, x squared plus 1 for x greater than or equal to 0. So to do that, let's begin by bringing into Maple the Student Calculus 1 package. There are many packages in Maple, over 100, and it's all part of the Maple library. It's just a way of organizing the Maple library. You get all of this stuff with Maple. It's not an add-on, it's part of Maple. Okay, so Tools, Load Package, Student Calculus 1. So that loads the package. Then I want to define this function. So I'm going to select f of x equals, control drag that down, f of x equals. And in the context panel, we see the option assign function. That does implements all the machinery that is required for Maple to define this expression, this rule, x squared plus 1, as the function whose name is f. Now there is a tutor that we can make use of, and you saw where the tutors are located, but I'm going to launch the tutor from the context panel. I do that by typing f of x, and I will do a control equal, which activates this option here, evaluate and display in line. So control equal. I think alt enter is an equivalent, but I always do control equal. So that echoes the rule. Then I go down to Student Calculus 1, and I have access to the tutors in Calculus 1 that makes sense to apply to this expression. Function inverse. So that launches the tutor with x squared plus 1 already in it. It has a default domain minus 2 to 2. Ours is x greater than or equal to 0, so we'll put a 0 there. So this is what the function and its inverse look like. This dashed line is the 45-degree line, and the color code here can be read from plot options. See where it says color? The function is in red, the inverse is in blue. So this is the piece of x squared plus 1 for x greater than or equal to 0. This is its reflection across the 45-degree line. It's the inverse function. And what is the rule for this inverse function? Well, Maple gives the rule for both branches, but this branch is clearly positive. It sits above the x-axis, so it's x minus 1 square root. if we select close, that will write that graph to our workspace. Now let's try to come to grips with the definition of the inverse function, where you reverse the order of the ordered pair x, y, y, x. Let's do that graphically. Maple uses a list, x, y. That should draw us a graph of the function. So let's just type that, x comma f of x. And of course, close the bracket. We do a control equal. We see in the context panel plots. We pick this tool called the plot builder. Plot builder comes up and gives us the option of drawing a 2D parametric plot. While it's drawn on a default minus 10 to 10, we would prefer this to be something like 0 to 1 or 2. Let's try 1. Okay, and let's adjust the view so that it goes from 0 to 2. Guess we've got to put a 2 in there. Okay, so this is a piece of the curve f of x, because that's f of x. Let's see what happens when the coordinates are reversed. But before we reverse the coordinates, f of x, x, in other words, yx, let's draw the 45-degree line. Now, the 45-degree line is xx. So let's just do x comma x, control equal, and let's draw the 45-degree line the same way. Plots, plot builder, 2D parametric plot. Let's have x start at 0. Let's let it go to, say, 2. And let's have the frame go from 0. Let's try 2, see if that's any good. Okay, so there is the 45-degree line. And now let's reverse the coordinates as the definition of the inverse tells us to do. F of x comma x, control equal, and let's draw a graph using the plot builder. So again, it's a 2D parametric plot, and we want x to go from 0. Oh, let's try 1 here, and let's have the vertical window be 0 to 2. Okay, now we want to put these all together. So let's copy and paste. And let's copy and paste. We have the same graph that the tutor drew. This is the function in red. This is the inverse in, I guess that's dark blue or black. And this is the 45-degree line. And the inverse is the reflection across the 45-degree line. And so graphically, here is an exploration of what it means to have an inverse function. Now finally, let's get a solution from first principles. Now, I always used to tell my students this mantra: set y equals f of x, solve for x, switch the letters. So what I'm going to do here in Maple is I'm going to switch the letters as I write the equation. Y equals f of x becomes x equals f of y. So I write x equals f of y. and I'm going to solve for y. So I get two solutions, positive square root of x minus 1, negative square root. And for what we saw in the tutor, and graphically, we want the positive branch, y equals root x minus 1. So now a problem from trigonometry. We begin with this notion of trig identity. Is this an identity? Is the left side identically equal to the right side? There is in the context panel an option to have Maple tell you straight off whether or not this is an identity. And so it's this option, test relation. Now Maple says true. And at this point I would say, well, this is some evidence tilting the needle over towards, yeah, this is an identity. But we don't know what Maple did, so it's probably premature to conclude that, yeah, this is an identity. But it might just be true. Now, I wonder if we can get some graphical, visual evidence of what this means to say this might be an identity. So let's graph this left-hand side. Can either steal it or retype it. I'll grab the right-hand side. We go to plots. And I think I'll just take a 2D plot. So there is a graph of the left-hand side. I right-click and take style point. I have a collection of points along that graph. If I take the right-hand side and drop it on to the existing graph, I get a graph of the right-hand side as a continuous curve. And so the points sit on top of that graph. And it would look like this graph is saying the left-hand side and the right-hand side, if graphed, are identical. So the values for each x on both the left-hand side and the right-hand side seem to be the same. Therefore, we have additional evidence, this time visual, that we are looking at an identity. Now we want analytic evidence that this is an identity. To do that, I'm going to begin by taking the right-hand side. Let's close this up here. The right-hand side and apply and expand. So basically we're expanding these cosine fourth and cosine 2. So here's expand. And when the appropriate trig formulas are applied, the right-hand side does become the left-hand side analytically. So digging a little deeper, we'll take each term separately. Let's expand cosine of 4x. And let's expand the middle term here, 4 cos 2x. And we see that if we add on this plus 3, we have a 1, that's 4, and a negative 4, they add to 0. 8 cosine squared, negative 8 cosine squared, they add to 0. What's left? 8 cosine fourth, which is the left-hand side. And so analytically, we see that yes, this is an identity, and the secret to verifying or proving that this is an identity is to use the expansion formula for cos 2x. After looking at trig identities, perhaps trig equations might come next. So here's an example where we're going to solve a trig equation. Well, it's quadratic in cosine, and we're looking for solutions in a fixed interval, because otherwise it would be an infinite number, or could be an infinite number. So suppose we draw a graph to see if a graph gives us some idea of what to do with this equation. How many solutions does it have, where they might be? So we want just the left-hand side, because you don't normally graph equations. So let's take the left-hand side. So this is what we want to draw a graph of. So plot builder. And we are drawing a 2D plot. And the default plotting range is minus 10 to 10, minus 2 pi to 2 pi. So let's just go 0 to 2 pi, because that's the range we're interested in. And we look and see there appear to be 4 solutions. 1, 2, 3, 4. Now, we've shown how the graphical tools in Maple could be used to read coordinates and estimate what those solutions are. But for now, let's just say, okay, there are 4 solutions, and we get a rough idea of what these 4 solutions are. With some rough idea of where the solutions are and what their values might be, let's get Maple to solve the equation numerically. So we need to grab the equation. It has an equation label, which we can use to reference the equation. You do it with Control L. L for label brings up the insert label tool. We type the number of the equation, and that stands for the equation. Let's try solve. And if we simply say numerically solve, we have no idea where Maple will start a Newton iteration. So instead, numerically solve from a point. And here we give a rough idea of an initial value, and we'd like to pick values near where we can see what these roots are. So let's try 0.6. And we have this first root, and we just keep doing that for the remaining roots. Control L1. Solve numerically from a point. So roughly, what is that? 3 pi upon 4. This is 1.57. So here, maybe we'll try a 2. We get a second solution, and just keep going. Control L1. Solve numerically from a point. Where'd that go? Solve numerically from a point. So we need another starting value. Let's try 4. And finally, Control L1. Maybe we'll try something like 5 for this one. Solve numerically from a point. Try 5. And we have a 4th solution. So that's one way to get Maple to solve numerically. Now let's get an exact solution to this equation. And to do that, we'll make use of the Student Calculus 1 package. So Tools, Load Package, Student Calculus 1. We did this before. Now, we want to get our hands on the equation. So here's a copy, or we could simply reference Control L1 as we did before. If we go over here to Student Calculus 1 in the context panel, we'll find the option Find Roots. And a dialog comes up allowing us to find roots in a given range. So that's 0 to 2 pi. And we're expecting to get an analytic closed form solution, so we will not check this box, calculate numerically. There are times when that is the appropriate thing to do. And so we have 4 exact solutions. And if we want to approximate those, let's approximate 10 digits, we see 0.8, 2, 4, 5. These are the numbers that we computed up here in the numeric solution. So this solution comes from the Maple Student Calculus 1 roots command, which will find all solutions in a fixed interval. Now Maple can also provide a general solution to this equation. So we need the equation. Let's reference it with Control L1. Go back to the solve option, and you see here solve general solution. So Maple has provided the general solution. There are 2 possibilities, and you'll see these symbols underscore Z and underscore B. The B is Boolean. It takes on the value 0 or 1. The Z is an integer, which takes on the integer values from negative infinity to plus infinity. So let's drag each of these expressions to a separate workspace. And substitute for B and Z the values listed here, 0 and 0, and 1 and 1. And the way I think I'll do that is I'll press the Enter key. I have a equation label that I can make use of eventually. Here I want to go to evaluate at a point. And in this pop-up, I can give the B parameter value 0 and the Z parameter the value 0. That gives me one solution. A second solution in this stream comes, let's see, equation label 16. So evaluate at a point. And the B value and the Z value, I will take 1 and 1. And this gives me the second solution that is in this chain of solutions. And I'm going to do the same thing here with the other member of the general solution. It has an equation label. I'm going to use evaluate at a point, again giving 0 and 0. This gives me a third solution. And the fourth one will come. I'll do Control L18 and supply the values 1 and 1 this time. Evaluate at a point, use 1 and 1. And this gives me the fourth solution. Now let's turn our attention to getting a solution from first principles. So we need the equation. So I think it had Control L1 would do it. And I'm going to select the left-hand side, and then I'm going to apply factor, because this is quadratic in cosine, and it factors into these two factors, and now I can use the zero principle, set each factor equal to 0, and solve. So there's the first factor. I want to set that equal to 0. And there are a variety of ways to solve this. One is to begin by selecting cosine. And you see up here it says isolate. So select that, and essentially Maple isolates cosine x equal to -1/2. The next thing to do would be to isolate the x, and you see x is 2 pi upon 3. And we'll do the same thing with the second factor. Set it equal to 0. Ooh, I didn't quite do that properly. I didn't put an equal sign in there. And you can see how it's easier to edit than it is to start erasing and crossing out on a piece of paper. So again, I'm going to isolate the cosine. Where did it go? Isolate the cosine, and then I'm going to isolate the x. And I get the second solution. Now there are 4 solutions, and at this point you need a standard quadrant analysis to march each solution into additional quadrants. Now this offhand remark about applying a standard quadrant analysis to get the other solutions, I think that's harder than it sounds. We know what the 4 solutions are. We know which 2 we got, which 2 we're trying to get. But let me show you what I learned in a trig class in high school many, many years ago. CAST. C-A-S-T. The cosine is positive in this quadrant. All functions are positive in this quadrant. Sine is positive in this quadrant. Tangent is positive in this quadrant. It's the first thing you got to get straight. And you get that by looking at the graphs and so forth. Then, this is a sketch. Remember, this is the first angle. Arc cosine 2/3. Okay? Arc cosine 2/3. How do you do this? Well, this is positive. So the cosine is positive in the first and fourth quadrant. So you take this angle as a reference angle in the fourth quadrant. The angle theta that you're looking for is then this one, which is 2 pi less phi. So it's 2 pi minus the arc cosine of 2/3. And if we go way back up here to where we got the 4 solutions, there's one, there's the other. And we just do the same thing now with this angle, 2 pi upon 3. Well, that's in the second quadrant. Now, in the second quadrant, the cosine is negative. So where else is the cosine negative? It's also negative in the third quadrant. So this becomes the reference angle. It will be pi upon 3, just doing simple arithmetic. So you draw that reference angle here, and the remaining angle that you're looking for is this one. So it's pi plus another pi over 3, and you get 4 pi over 3. Okay? This is what I learned 65 years ago when I was in high school in the mid-50s. I don't think that this is trivial. I think it takes quite a while for a student to learn that. I can't see squeezing that into all of that into one course and expecting the student to master that overnight. This is why I think if you want to get that much material in one course, you've got to use a tool that will tell you stuff like we see here, given by Maple. Uh, Otherwise, it just takes too much soak time for this stuff to sink into a student's head. They need a tool like Maple in order to make sense out of all of this material in a short time. Someplace in the Precalculus course, student runs across the binomial theorem. Let's take a look at what Maple can contribute to that discussion. So we'll use the binomial theorem to expand this fourth power binomial. To begin, let's just take this expression and have Maple expand it. So using the context palette, we'll do an expand. And this is what should happen if we apply binomial theorem. Binomial theorem requires a sum. Now we have a sum operator here. It comes from the expression palette. Expression palette has it in here somewhere. There it is. Okay. Now I have it in my favorites palette. Favorites palette starts out empty. You populate it with what you want to put in there. And the way you put something in there is you right click on it and you have the option add to favorites. So that's how you populate the favorites palette. So we need a sum. I like K as my index, and K will go from 0 to 4. And what goes in there? Well, you need a binomial coefficient. Well, binomial coefficients are up here in the expression palette, right there. So it's 4, choose K, and then a right arrow to come out, then a space for multiply. Then you need a parenthesis because you're going to put in 2x. Now you can raise that to the K. The next factor, which is 3y, would be raised to the 4 minus k. That's the binomial theorem. Does it give us the same expression? Yes, it does. So there you have two different ways of looking at this expression. Expand it in Maple, and then apply the binomial theorem and see if you get the same thing. Unfortunately, there's a bit more to the use of this binomial theorem. You have these choose symbols, right, with permutations, combinations, all that stuff. Then you get dragged into Pascal's triangle, binomial coefficients. It's a bigger issue than just the phrase binomial theorem. So here's a little gadget I put together. The slider controls how many levels you're going to come down, and I'm building Pascal's triangle. Right? One's on the outside. Add adjacent numbers, get the number below the space. Okay. 1 and 2 is 3. 2 and 1 is 3. I took it out to 10. 1 and 8 is 9. 8 and 28 is 36. So a student has to first be exposed to Pascal's triangle as a way of getting these binomial coefficients. And these numbers are actually from these binomial coefficient choose symbols. And there's another widget here that I put together to explore those. Okay, so n choose k, n factorial, or k factorial, n minus k factorial, and here are two sliders controlling n and k. So the symbol n has 7, k has 4, so you see 7, 4, 7 factorial, 4 factorial, 3 factorial, that evaluates to 35. So here's another way for a student to get some confidence, some experience, some insight into what this symbol means. I think we have a chance to take a quick look at an induction problem. Let's prove by induction that the sum of the integers from 1 to k obeys this formula, k plus 1 over 2. Well, what's the pattern to a proof by induction? Well, essentially you show it's true for a couple of cases, then using the truth of the statement for case n, you show it's true for n plus 1. All right, to do that, we're going to begin by taking this general statement, bringing it down here. Now, we want to make the left side inert. So to do that, we select it, go down here to 2D Math, convert to inert form. When I press the Enter key, you'll see that the left side, the summation, is in gray, meaning that operator is now inert. And we will need this statement several times. For example, we want to check that this is true for a couple of cases. So let's check it for k equals 2 and k equals 3. So to do that, Control L, because we're going to use the equation label to reference this thing. Right? And then evaluate at a point and let k be 2. And you see that if you sum 1 plus 2, you're going to get 3. Well, that's a true statement. Let's try it for one more. Control L1. Evaluate at a point. Let k be 3. So 1 plus 2 plus 3, I believe that's 6. So now you need to take the general statement. So what is the general statement? Here's the general statement. Now what does this look like when k becomes k plus 1? So what does the statement for k plus 1 look like? So you evaluate at a point, let k become k plus 1. So this is what the statement at k plus 1 looks like. Can we use the statement for k to show that the statement for k plus 1 is true? So let's go back and take this statement for k, Control L1 or 4, either one. Now, I want to take that right-hand side, because to that right-hand side, I want to add k plus 1. So Control L7, that gives me that right-hand side. And let's add k plus 1. Now, does this become this? Well, it requires some math. Factor does the job. So factor, this expression is the kth statement plus one more term, k plus 1, and that establishes the truth of the k plus first statement. And that's the typical pattern for induction proofs.